Hello, AP Chemistry students. We've now arrived at Unit 3, and this is Section 3.1 on intermolecular forces. So our learning objectives here are to explain the relationship between chemical structures of molecules and the relative strength of their intermolecular forces when A, the molecules are of the same chemical species, and B, the molecules are of two different chemical species. So we've talked a lot before about intramolecular forces, and we've talked about these mainly in terms of the covalent bonds in molecules, which are electrostatic or Coulombic forces. Electrostatic is just sort of a fancy word for describing the force between two charged particles at set distances from each other. And these forces are really important because they tell us about the chemical potential energy contained within the bonds and also the polarity of the molecule, how much the electrons are being moved towards one side of the bond, creating an asymmetrical distribution of electrons. So now we're going to be talking about intermolecular forces. And if we break down the English of this, the prefix is intra versus inter. Intra usually refers to something within, and inter refers to between. So imagine a scenario where you have two water molecules. The intramolecular forces are going to be the covalent bonds between the hydrogen and oxygen atoms that are holding the molecules together. And then the intermolecular forces are going to be the forces that attract the two adjacent water molecules. We know that water has a good tendency to stick to itself, and this is based off of the intermolecular forces. And this is also an electrostatic or Coulombic force, but instead of talking about the bonds themselves, the intermolecular forces have a large impact on the macro scale properties of the substance, like the density, the liquid surface tension, the melting or boiling point, the miscibility, which is the tendency of the substance to mix with other substances. And overall, these forces describe how well a molecule is at sticking to itself and to other molecules. So there are three tiers of intermolecular forces, which from now on I'll probably notate as IMFs. And they are the London dispersion forces, the dipole forces, which there are a few different versions of, and then hydrogen bonding. And to analyze what kind of intermolecular forces are present in a molecule, you want to know about the overall polarity of a molecule. So when you're determining this, you're going to want to be familiar with how to recognize polar covalent bonds and how polar covalent bonds affect the overall geometry of a molecule. Or sorry, the other way around, how the geometry is impacted by whether the bonds are polar or not, and how that means the electrons are asymmetrically distributed or symmetrically distributed. So let's talk about the London dispersion force. So this is the weakest and most fundamental of all of the IMFs. And what I mean by fundamental is that this exists in all molecules, regardless of what kind of molecule it is. It just happens to not be the most prevalent force in a lot of molecules. And the mechanics of how this works is due to the random movement of electrons. So we've talked about the Schrodinger model of the atom and how we have all the different subshells that all have different shapes and how those subshells represent different volumes of an electron cloud and where those electrons could be at any one point in time, which means those electrons are able to sort of teleport around. And that means that at some points in time, you have a symmetrical distribution of electrons, and at other points in time, you have an asymmetrical distribution of electrons. So if we refer to this figure here, here we have the three electrons that are evenly distributed, and then here we have all of the electrons that are randomly now on one side of the atom, which creates a temporary dipole because we have a partial negative charge where all the electrons have grouped up, and then we have a partial positive charge where we now have the bare exposed nucleus, and we have basically bare protons being unshielded by a cloud of electrons. And this creates a really, really instantaneous temporary dipole because these electrons are just going to teleport away again. So how this ends up holding molecules together is through an induction effect. So if you imagine that all of these electrons have moved to this side of the atom, and we have this now partial negative, and say that atom comes in contact with another atom whose electrons are still symmetrically distributed, that negative charge here will then attract or it'll repulse the electrons to the other side of the atom, and then you'll have like a negative, positive kind of alternating effect. And this creates sort of a domino chain reaction sort of effect. And this ends up being enough to hold some nonpolar molecules together. But as you'll see later, substances that rely on just this force to hold it together are generally going to have lower boiling points and lower melting points. Another thing that's important to note about London dispersion forces is that even though this is the weakest of the IMFs, The LDF force, or the London dispersion force, can get stronger the more electrons are available. And when we talk about an atom having more electrons, or a molecule having more electrons, we describe it as being more polarizable. There's more probability of the electrons being moved to one side. And also, the more electrons are being moved from one side to the other, the stronger the dipole is going to be, and therefore the stronger the force is going to be overall. And this ends up explaining a lot of sort of macro scale properties that we notice about different substances. If we think about fluorine, chlorine, bromine, and iodine in their elemental diatomic states, at room temperature, fluorine and chlorine are gases. Bromine is a liquid and iodine is a solid. And that has to do with the strength of the London dispersion forces in these four nonpolar molecules. Iodine has a lot more electrons than bromine does, and bromine has a lot more electrons than fluorine and chlorine. And because they have more electrons, that means that LDF force is stronger. And that's why iodine is able to hold itself together as a solid at the same temperature at which bromine is a liquid, and at the same temperature which chlorine and fluorine have overcome their intermolecular forces overall and have become gases. It also explains why methane, CH4, the type of gas that is in a gas stove, is a gas at room temperature. Octane, which is made of the same atoms, but more of them. Methane is CH4, octane is C8H18. This is a liquid at room temperature. And then something like paraffin, which is what wax is made out of, which has 40 carbons and 82 hydrogens, is a solid at room temperature. The bigger the atom, the bigger the molecule, the more electrons are available, the more polarizable it is, the stronger the instantaneous dipoles can be, and overall, the stronger the London dispersion forces are. One other point to make about London dispersion forces is that they are also made stronger by the presence of pi bonds. So we talked about sigma and pi bonds, and we were talking about hybridization of molecular orbitals and how sigma bonds are in the axis of the molecule, meaning the main connection between the two atoms, and that pi bonds are made of these leftover p orbitals that sort of overlap out of axis. And this ends up making a molecule more polarizable as well, because these electrons that are in these pi bonds are sort of further away from the nucleus. They're not in the direct connection between the two atoms. Rather, they're in these leftover p orbitals that have kind of bent in to overlap. And having more pi bonds makes London dispersion forces stronger because these electrons are technically sort of farther away from the nucleus and therefore less attracted to the nucleus. And then it makes them more probable to be polarized by outside molecules coming in contact or bumping into this substance. So let's move on to the dipole forces. So there are three different dipole forces that I'm going to talk about. One is the dipole-induced dipole force, the dipole-dipole force, and the ion-dipole force. All three of these are named after the two things that are being attracted to each other in the force itself. So let's go over these one at a time. These forces work generally the same way as London dispersion forces, where you have a dipole, you have a positive and a negative side that are going to attract the unlike charge, kind of like magnets. But the big difference between dipole forces and London dispersion forces is that in London dispersion forces, we have very temporary dipoles, but with dipole forces, we have permanent dipoles. So in the dipole-induced dipole effect, we have a very polar molecule that has a permanent dipole in it, which is going to come in contact with something nonpolar. Generally something nonpolar that's highly polarizable, meaning it has many electrons. And in this case, we have a xenon atom. Xenon has a ton of electrons. So we have a water molecule here, which has a strong dipole pointing towards the oxygen side of the molecule. So we're going to have a strong partial negative charge on the oxygen. And when that bumps into the xenon, it's going to induce a dipole, much like it did in the LDF, where the electrons are then suddenly going to be moved to one side of the molecule, and the xenon is going to gain a temporary dipole where it did not have one before. And this is going to cause a force of attraction between these two substances. In a lot of diagrams, you'll see dotted lines between two substances. That's usually how we show intermolecular forces in diagrams. And this dipole-induced force is much like the LDF force, is going to get stronger the more electrons are available to be polarized, and the stronger the permanent dipole is in the polar molecule that is involved. So for a dipole-dipole force, this is sort of the most basic of these types of forces, where we have two polar molecules that have a permanent partial negative side and a permanent partial positive side, and then they're just going to be attracted to the opposite charge on the adjacent molecule. So in this case, we have hydrogen chloride. Chlorine is more electronegative than hydrogen, so all the electrons are going to be pulled towards the chlorine side of the molecule. And then the chlorine side of the molecule is going to be attracted to the hydrogen side of a molecule on an adjacent one. And much like in earlier cases, the stronger the dipole is within the molecule itself, the stronger the force of attraction is going to be between the adjacent molecules. So the last of these dipole forces is the ion-dipole force, which occurs when we have a cation or anion that comes in contact with a polar molecule. So here we have an anion, which is negatively charged, and we can see that's going to attract the positive side of a polar molecule. And then the vice versa situation is going to happen with a cation. It's going to attract the negative side of a polar molecule. And this ends up explaining why there's such high solubility for some ionic compounds. For example, say you have sodium chloride, table salt, and you put that in water. The sodium chloride is going to separate into its component, sodium and chloride ions, and then the water molecules are going to sort of align themselves based off of the charge. Here we can see that the sodium cation is going to attract the negative sides of the water molecules, and they're going to surround it in what's called a hydration shell. So all of the sodium ions that are floating around in solution are going to gain a little shell of water molecules that are oriented with the oxygen facing the sodium ion. And then the opposite happens with the chloride ion. Because it's negative, it's going to attract the positive side of the molecule. And you can see the hydration shell here has all of the hydrogens sort of surrounding the negative part. And this also explains why these things dissolve in the first place, because if you put some solid sodium chloride into water, all of the water molecules are going to sort of surround it at the surface and start to pull the ions out of the ionic lattice and surround it in these hydration shells. And in a lot of cases, this is going to be a more stable situation. All right, so the third type of intermolecular force that we're going to talk about is the hydrogen bond. Personally, I hate this word, hydrogen bond, because a lot of people hear the word and think that it's a covalent bond. They think that it's a intramolecular force, when it's actually describing an intermolecular force. It just happens to be involving hydrogen. And this is also just a dipole-dipole force, but it's a very specific type of dipole force that makes it extra strong. So we only really have hydrogen bonds when first we have a hydrogen, obviously, and that hydrogen is going to be attracted to one of the three most electronegative elements, mainly fluorine, oxygen, and nitrogen. And what's going to happen in all three of those cases where hydrogen is bound to one of those three electronegative nonmetals is that these are so electronegative that they're going to pull away the single electron that hydrogen has. And in that bond, we're going to end up with a really strong dipole because hydrogen only had one electron to begin with, and it's being practically almost pulled away, almost like an ionic bond, but just not quite that strong. But what results is a bond where hydrogen just becomes basically a bare proton. So we have a strong positive charge on the hydrogen side, and then the fluorine, oxygen, or nitrogen, which already was hoarding electrons, is going to become even more negative. And we're going to have a really strong dipole interaction between adjacent molecules that have this type of bonding. So make sure that when you're trying to identify hydrogen bonds, that one, you obviously have a hydrogen, and then also it has to be directly attached to a fluorine, oxygen, or nitrogen. Say you had a molecule that had hydrogen attached to carbon and then carbon attached to fluorine, that would not be considered a hydrogen bond because the hydrogen is not directly attached to that electronegative element. And these are considered to be the strongest type of intermolecular force. I already explained what is on this slide, so I'm just going to move on. All right, another thing that's interesting about hydrogen bonds is it explains why ice floats in water. If you think about different substances, if you think about different substances in their solid and liquid forms, most solids are going to sink into a liquid of the same chemical, but water molecules are unique in that ice floats on top of water. And if we break this down to the molecular view of this substance, because water has these really strong hydrogen bonds, they end up forming this lattice that is sort of hexagonal, and it creates a lot of empty space. So overall, the density of ice is lower than the density of liquid water. As they're moving around and being able to freely interact with each other, they're able to get in a lot tighter. And then that's why, because there's more empty space and there's going to be less mass per unit volume, that is why ice ends up being less dense than liquid water. All right, so on average, if we're comparing molecules of similar size, the hydrogen bonds are going to be the strongest, the ion-dipole are going to be the second strongest, followed by dipole-dipole and dipole-induced dipole. And then lastly, the London dispersion force is the weakest overall. But like I said, when we're comparing molecules of similar size, because even though the London dispersion forces are weak, they can become a lot stronger if the molecules are sufficiently big enough and have more electron cloud surface area. A good way to think about it, here let's compare N-pentane to 2-methylbutane and 2,2-dimethylpropane. If you think about just the overall surface area of these three molecules, even though they're around the same amount of mass, this one has more exposed like electron cloud, more surface area of electron cloud to interact with other substances, which means it's going to be more polarizable. And you can see as a result, the boiling point of this substance is 36.1 degrees Celsius, whereas these ones are 27.9 and 9.5 respectively. So the more surface area of electron cloud and the more electron cloud overall, the more polarizable and the stronger those London dispersion forces are going to be. So let's do a quick practice now. Let's look at these four molecules and try to determine what kind of forces are going to be involved based off of the structures. All right, take a moment and think about this on your own. Maybe pause the video. All right, so from this, we can see that the NH3 is going to have hydrogen bonds because we have hydrogen bound to nitrogen. We're going to have a strong dipole pointing towards the nitrogen, and we're going to have sort of an amalgamation or a gathering of electrons on this nitrogen. This is going to be trigonal pyramidal, so the geometry is not going to make these forces cancel each other out. And I included LDF here just because technically every single molecule has London dispersion forces, but the hydrogen bonds are going to be the main force holding these NH3 molecules together. All right, now let's look at carbon tetrafluoride, CF4. This is just going to be London dispersion forces. Even though the carbon-fluorine bond is highly polar, you can see because of its tetrahedral geometry that all of these forces are going to pull in opposite directions and therefore cancel each other out and not have a net dipole overall. So this is going to be a nonpolar molecule, which means it's only going to have access to London dispersion forces. All right, and now let's look at CFH3. So similar molecule, similar tetrahedral arrangement, but now we have three hydrogens and one fluorine, and this is going to be dipole-dipole because the carbon-fluorine bond, as we just discussed earlier, is going to be a highly polar bond. The electrons are going to move towards the fluorine here, and then we don't have forces canceling that out like we did in the CF4 example. The hydrogen is less electronegative than the carbon, which means all of the dipoles are going to point sort of in one direction on this molecule, which means that this is going to be a polar molecule overall. And because it has a permanent dipole in the molecule, this is going to be attracted to itself through dipole-dipole interactions. So the two polar molecules are going to be attracted to each other with their opposite positive and negative sides. And as always, I included LDF just because everything has LDF. All right, and then lastly, this ICN molecule. This is going to be dipole-dipole as well because it's asymmetrical. We have three different elements. They all have different electronegativities. There's no way this bond and this bond are going to cancel each other out, though this is probably going to be a very weakly polar bond because the carbon is probably going to be more electronegative than the iodine, and then the nitrogen is going to be more electronegative than the carbon. So we're going to have a bit of a pull in this direction. And overall, this is going to be a dipole-dipole force. The last thing I want to say, which I'm going to talk about more in later lectures, is that intermolecular forces are also really important to biological molecules, the very, very large biomolecules like proteins, because generally how a protein is arranged is you have a long chain of what are called amino acids, and this long chain ends up raveling itself up into big globs where it's all tangled in itself like knots. And the thing that's holding these knots together are the intermolecular forces of adjacent parts of the chain. But we'll talk a bit more about that in a later lecture. So I'll see you in 3.2.